Hello, my name is Alexey Kravets. I work in media processing division at ARM. First of all, a few words about ARM. ARM is, I think, well-known company for which designs processors for embedded systems, and the rest, ARM also designs GPUs uh, for mobile devices, and recently ARM entered GPU market. Uh, these are the set of existing devices in the market where you can try ARM GPUs with OpenCL support. I'm trying to be a bit quicker. So, CARP project. CARP is European funded project aiming to solve two problems of GPU programming. The first problem is that a GPU, in particular OpenCL code, is not really portable and not performance portable. Yeah. So in order to to design a correct and efficient GPU program, you need to target particular device or particular set of devices. I'll talk about it a bit more during the rest of the presentation. So the first goal is to target the performance portability, and the second goal is to target the verification of existing OpenCL kernels. So the expected impact of the project is to increase the productivity of the development by avoiding the necessity to use low-level OpenCL and replacing it with some high-level domain-specific languages, which may target specific computing areas. In order to demonstrate the project, the proof of concept phase feature tracking application will be developed, and using the domain-specific language developed for this application, and proof of concept linear algebra DSL will also be demonstrated on the early stages of the project. So there are how many? 7 or 8 different companies involved. Since it is UK multi-core conference, I'll concentrate on Imperial College London and ARM. And ARM monoidics are really connected to our current work, so I'll talk mostly about Imperial College London and ARM, of course. First of all, Pencil. In order to reduce the amount of work for adding new DSL or adding new GPU device, the platform neutral computational language, kind of intermediate representation for the whole pipeline, is to be designed. So basically, the approach. Can I? Yeah. Yeah. Basically, basically the approach is the follows. There are a set of domain-specific languages designed to target particular problems in particular fields. They all are transferred by the language-specific backends to Pencil. Then set of cross-component optimization of the Pencil representation is applied. Then the optimized Pencil is transferred into OpenCL using the machine learning technique and feedback from the devices. So multiple OpenCL kernels can be produced for one Pencil function, and the best of the kernels will be selected. Only a best based on the performance of the transformation tool. So I think I mentioned that there are a lot of DSLs and there can be a lot of DSLs and a lot of target devices, and designing M times M compilers is a great waste of time, energy, and so on. So having the general intermediate representation reduces the amount of work. Most modern compilers use this technique. So Pencil. Pencil is performance-oriented. The goal of the language is to have some language which is a bit lower than DSL, because it should be general, but it also should preserve every meta information which is present in the DSL. For example, if you have indirect memory access, which is known to be to be dependence free in a loop. This kind of information can be directly stored in Pencil. Currently, Pencil can be implemented as a subset of C language with additional meta information via annotations. In order to design Pencil, we analyzed two OpenCL benchmark suits to get the ideas of what kind of problems are solved using OpenCL. We analyzed Rodinia benchmark suits, it's 16 benchmarks, and Shock. There are actually more benchmarks in Shock than at present here, but these are the benchmarks from Shock level 1, which are not so simple as level 0 and not so complex as level 2, basically. Just to give you a brief approximation, the document containing which contains the analysis of this with 21 benchmark is like 255 pages. For example, this is not the analysis of the real benchmark, because real benchmark analysis is like 10 or from 10 to 12 pages. For example, matrix multiplication. First of all, the high-level description of the particular algorithm used to solve the problem is given. We give the algorithm, which is this nice formula. We describe data structures, iteration space, which is quite simple. Dependencies. In this particular case, we don't have usual dependencies. We have only the reduction in the inner loop. But in general, there are there are dependencies between iteration, which I mentioned here, and also it's memory access information. For every iteration, MR denotes the set of memory allocations. In that case, memory allocations are defined in terms of data structure described above. So, for example, in that case, on each iteration ijk, the A ik and B kj G is read and Cij is written. And we describe low-level implementation details. First of all, concrete implementation data structures is described and mapping between high-level and low-level data structures is given. For example, as you can see, this data structure, original matrices, are implemented as two-dimensional arrays on host and as one-dimensional buffers on device. For every kernel, the pseudocode abstraction is given. It may seems a bit like usual OpenCL kernel, but we try to make it a bit higher level to show the actual algorithm rather than some low-level things. For example, we have specific notation for global IDs, which is this gamma notation, in order to avoid repeating stuff like calling get global IDs. We also present concrete iteration space and mapping between concrete and abstract iteration spaces. This memory access information and evaluation metrics. Evaluation metrics includes the size of the input data and what's actually measured. In that case, it's not present here, but for example, it might be something like the total device computation time is measured. But it was a very small and simple example. The real benchmarks we analyzed include some more interesting cases, like graph traversal algorithms, which requires analyzing graph representations suitable for parallel computing, sparse linear algebra, sorting algorithms, which also cannot be directly mapped into GPU and require some modifications. A lot of grid computations. I'll talk about them a bit more, and more complex dense linear algebra. For example, for Gaussian elimination, which is iterative algorithm, it cannot be mapped to single kernel call. So it's implemented as a set of kernel calls with synchronizations between iterations. So optimizations. There are some
common optimizations present in most benchmarks. Like, for example, some algorithms are implemented as iterative computations. For example, some computations over grids. So the initial data is supplied via input file, so generated. Then every iteration of the computation computes the data based on the results of previous computation. So basically like this. Each iteration is performed at a single kernel large. So some benchmarks which copy memory from output buffer to input buffer. The different way of doing it is to swap buffers logically using the CL set argument call, which is a very simple optimization. Ghost zone optimization, which is more interesting. For example, having again computation over grid, and the orange blocks are blocks computed by one OpenCL group, and the blue blocks are blocks computed by another group, and the arrows denotes dependencies. So basically, in order to compute the second row, each group requires element computed by the different group. Since inter-group synchronizations in OpenCL are generally not supported, it requires some effort to do it. It can be done by making each call compute only one row, or making every group compute some additional boundary values. It increases the amount of computations because some values are to be computed twice. For example, the squares which are both blue and orange will be computed twice, but the computation can be done without synchronization. Gala usage. If again, for some grid computation or image processing, the boundary conditions checks can be quite painful because they make the they require conditional jumps which are not very good for GPUs. There are several ways of dealing with this problem. Basically, you can add checks, which is not really efficient. You can increase the size of the image and add some fake data, which can make the memory X and the algorithm unified. So you start not from index 0 but from index 1, but in that case you can safely access I-1 element of the array, make the computation unified. You can also use CL image type, which can deal with such issues. This is an interesting question: coalescing and data locality. OpenCL standard says nothing about coalesced memory access, which is important. For example, consider the following loop. There are two memory accesses here in the loop. The first access is coalesced, but for NVIDIA, it's okay. But for OpenCL, it's not that clear, because for the second memory access, the data access in one thread is very local, while in the first line, the distance between memory access is equal to n, which can be quite big. So which one to choose depends on your hardware, whether it supports coalescing or not. The same about local memory usage. For example, ARM GPUs uses unified memory space for local and global memory, so there is no point in copying some global data from local memory. Local memory usage has another advantage. You can rearrange the data. For example, if you're doing blocked matrix multiplication, you can have your second block transposed, if it helps. Most benchmark uses parallel reduction implementation. I think there are plenty of algorithms of doing this. none of the benchmark actually uses vector operations, which are currently supported by some OpenCL devices, like ARM Mali, starting from ARM 600. Of course, there are some problems. Most benchmarks lack any validation mechanism, which leads to another bunch of problems. Some benchmarks have inconsistent synchronization, like using out-of-order OpenCL calls to implement like overlapping between computation and memory transfer, but using in-order common queue, which makes every computation doing one by one without any overlapping. Some benchmarks spawns much more work items than necessary. For example, processing the single row of the two-dimensional array, which requires n threads. The n times m threads is spawning, and most of the threads just do nothing. They exit by a guard condition in the loop, in the kernel. So the kernel starts if the global ID is less than m, then do something, and the actual work size is n times m. There are some specific application bugs which have been discovered, reported, and fixed in the Rodinia and Shock. They maybe not fixed now, but they promise to fix it in the future releases. Like incorrect translation from two-dimensional indices into one-dimensional. This is where the actual mapping between high-level and low-level data structures is helpful, because we have a mapping which is which we extract by analyzing the algorithm. Then we have the actual kernel code, which has the different mapping. So we just to check whether our computations are wrong or the mapping in the kernel is not correct. So a few words about the pipeline and example. In order to demonstrate the pipeline, the proof of concept linear algebra DSL is designed and implemented and under heavy development now. For example, this DSL is designed purely for implementing base linear algebra subroutines. So it's kind of focused on linear algebra. For example, vector-vector multiplication can be expressed either by sum function or just multiplying two vectors. Matrix vector multiplication is a bit more tricky, but still. So the features of the language is that any arrays of the same sizes can be added, and any array can be multiplied by the constant, by a scalar value. Basically, it's like this. We'll have more interesting example. Yeah. For example, complete example, the same matrix multiplication. So the LAD implementation is a correct program which can be compiled by our compiler into pencil implementation. So as I said before, pencil is something similar to C language with additional notations. So yeah, this is not really good implementation because it has a function call, but the function call serves the purpose to show the concept of access functions. The sum function code is quite straightforward, except the access function notation. Access function serves, for example, if the compiler isn't smart enough to figure out the memory access patterns in the function, programmer or the cell compiler can supply the function implementation with access function, which simplifies the original function and gives the information about the memory accesses. In that case, it seems pretty similar to the original function, but as you can see, there is no actual operation, just use and def macros, which helps the compiler to figure out the actual memory access patterns. After the domain-specific language been transferred into Pencil been cross-optimized, and then the Pencil code is transformed into OpenCL code. This is done by polyhedral parallel code again. This is a polyhedral OpenCL code generator designed by currently designed by ENS in France. So basically what they are doing, they extract polyhedral model from Pencil code, analyze it, like determine the dependencies which are not supplied by Pencil annotation, and design the scheduler for for the computation. Then they generate multiple OpenCL kernels and uses machine learning technique and feedback from computations on the model input data to select the best kernel. This is kind of weird slide because it has this very funny baseline parameter. Actually, the sequential CPU execution denotes Intel Xeon E5530 with 2.4 GHz. The second part of the project is verifier for GPU kernels. We assume that our compiler is correct, but there are a lot of incorrect OpenCL code, as I showed earlier. Even OpenCL benchmarks, which some of them are going to be included into specs, they have plenty of problems. So GPU verifier for GPU kernels originally been developed in Imperial College London and Microsoft Research. Currently, the work is continued as a part of the CARP project. It can prove absence of some defects and also verify assertions. For example, we have this buggy kernel. If offset is smaller than local group size, we have race condition, which is reported by not race condition, data race, and which is reported by GPU verify. This is a very simple example. Adding global memory barrier solves the problem, which is verified by GPU verify. GPU verify is based on the on the Silang front-end from LLVM. Basically, it builds the sequential representation of the OpenCL kernel. Then it tries to figure out a loop invariance and prove the correctness of this invariance. It been trained on set of kernels, sometimes with manual help of the programmer to figure out the loop invariance. After that, it's been applied to another set of OpenCL kernels. So basically, it's NVIDIA SDK for training and AMD SDK for verification, with about 70% success rate. And with quite reasonable response time, because if GPU verify is to be used in the continuous integration process, like you're writing a kernel and verifying it while you're developing, it's impossible to wait like several minutes for every line of code. So summary: there is a low-power GPU hardware, which is ARM GPUs, and the CARP aims to address this issue about the GPU programming, that GPU programs are not performance portable and sometimes is not portable. For example, we have CUDA-specific calls in OpenCL kernels. It's been clear that this kernels has been just converted CUDA code. So kernels assume that they have lockstep executions. Some kernels even have sync thread calls, which somehow works for NVIDIA OpenCL implementation, but definitely doesn't work for AMD OpenCL implementation, and of course doesn't work for ARM OpenCL implementation. So don't hesitate to contact us if you're interested. Yeah, that's it.
So 1 or 2 questions for Alexey before we. There's one down at the front on that side. If you can get there, thanks.
Hi, just wondering if the Pencil framework there is that similar to the OpenACC or OpenMP extensions in sort of its philosophy of what it provides?
Currently, Pencil is under development, so this is just a draft version. Yes, it's influenced by this framework. I think mostly it's influenced by OpenMP. I think the idea is to reuse existing C parser.
So what would the sort of the differences be between the two approaches, or the similarities?
To be honest, Pencil is designed not by us, but by INRIA in France. So we don't have the full background. As we discussed it, yeah, I think they really don't want to modify their existing parsers. So I think it's the fact that it looks very similar to OpenMP is partially influenced by this.
One more question. Over here.
Hi, Jonathan Hogg, SCFC. So I don't know how much you are interested in the stuff which goes on sort of between Pencil and what you get out the end in terms of runnable code, but a lot of things like the density algebra BLAS is characterized by having multiple implementations depending on the values of, say, Mn and K for matrix multiply. Do you envisage outputting different code for different parameters to the function?
Yes, it's possible. Basically, the idea is to have the general implementation, which is high-level Pencil, and the set of input parameters, which includes the algorithm parameters and the device parameters, and generating one or multiple kernels based on these parameters. Then these kernels will be verified, and the best for this particular set of arguments will be selected.
Well, we'll leave it there. So let's thank Alexey once more. Thank you.